ray tube. It's accelerated through a potential difference of 10 kilovolts. So it starts here at one side where it's 0 volts, passes through to the place where it's 10 kilovolts. Then it goes through an area of magnetic field that has a width of 2 centimeters. And the question is, find out how big is this magnetic field so that the electron deflects down this way, and the amount it deflects by in the end is equal to an angle of 10 degrees. So our strategy here, what we're going to try to do is the electron goes from here to here. So that's a pretty standard problem that we did back in chapter 26, I think, maybe 25. It's a conservation of energy problem. Starts here, is not moving, ends up over here, gets accelerated by the field, and it is moving, so we can find the speed here. Then we come to a magnetic field problem. It comes into this field. It's going to feel a magnetic force. Because of that magnetic force, it's going to have an acceleration, so the velocity is going to start to change. So we can apply the idea that F is qv cross b, find the force, from the force find the acceleration, from the acceleration find the velocity. Then we compare this velocity to that line that goes straight through, knowing that that angle is 10 degrees, and see if we can sort out b. So that's our plan. Conservation of energy here, magnetic force here, throw in a little bit of kinematics to find v, and then a little bit of trig to find b. So let's start with the first part first, and I think maybe rather than draw here, I'm going to draw new diagrams as I go. So the first part is going to be conservation of energy. So there's our 0 volt plate. That's the initial potential. Comes over here to where the final potential is 10 kilovolts. We have a negative charge here released from rest, starts to move this way. We'll write down conservation of energy. Final energy is initial energy plus work done by non-conservative forces. Work done by non-conservative forces here is 0. We don't have anything like friction. So final kinetic plus final electric potential equals initial kinetic plus initial electric potential. Let's ask what are each of those terms that we're going to fill in. Final kinetic energy, Kf equals 1/2 times m times v squared. That's going to be the speed when it's right here. UEF equals charge times final potential. This is an electron, so the charge is minus the fundamental charge. K initial is it's released from rest, so it's 0. UE initial is charge times initial potential, so also 0. So let's put these things in over here, see if we can find that speed. So 1/2 times m times v squared minus e times vf. Trying to be careful with my v's here. This little one is for speed, this big one is for potential. Equals 0 plus 0 equals 0. So the speed when it's at this point right here is equal to e times final potential over 1/2 times m. Take the square root. What do we have to put in here? VF equals 10 kilovolts. 10 kilovolts is 10 times 10 to the 3 volts, because kilo means 1,000. M is the mass of the electron, 9.11 times 10 to the minus 31 kilograms. E is our fundamental unit of charge, 1.6 times 10 to the minus 19 coulombs. Okay, you can leave this as an expression if you prefer. I think if we go with expressions, it might get a little bit tangly, so I'm going to fill in a number here. I get for the speed 5.93 times 10 to the 7 meters per second. Okay, so there's the speed as it enters the second magnetic field. For comparative size, it is less than the speed of light, so we're good there. It is pretty fast, but then it's a pretty small particle going through a big potential. We expect that that speed is going to get fast. Okay, next step of the problem. We have our electron right here, and it enters this magnetic field. The magnetic field points into the page. Let's get some vectors on here. The velocity with which it enters the field is the v that we just found. So if it enters this field with this velocity, what's the direction of the force on it going to be? So the force is the next good thing to think about. Let's get the direction of the force first. So our thumb goes with our v, our index finger goes with b, and our middle finger shows our force, shows the force pointing towards the top of the page, but it's an electron, it's a positive charge, so we have to rotate our answer by 180. So the magnetic force points down. I'm going to put that on the diagram too. There's FB. Okay, let's find our FB, or find an expression for our FB anyway. So we know that FB equals Q times V crossed with B. So how are we going to write this down? Well, let's think of what we know. Q is equal to minus E. Our velocity vector is the magnitude of the velocity we found above. It's moving to the right, so that's that velocity to the right, or I hat. B is the magnetic field. It points into the page, and it has some magnitude that we'll call B. Okay, so now that I've written this down, let's get our coordinate system in here. Positive x is to the right, positive y is up, and positive z is out of the page. B is into the page, so that's negative z. So let's see what we have here. I think I'll go symbols first, just to write it down with our direction, and then we'll get our answer. So we've got minus E times V I hat crossed with minus B K hat. Okay, minus and minus gives us plus. EVB I cross K. We ask, what is I cross K? You may remember, or you may use a little mnemonic to help you remember. I cross K goes the opposite way around the circle, gives us minus J. So we did with our right-hand rule that the magnetic force points down. That's verified by using our math here, doing the cross product. So we'll plug in what we know. E is 1.6 times 10 to the minus 19. V is the magnitude of the speed here, 5.93 times 10 to the 7. B is just B. We don't know that yet. We're trying to find B. And the direction is J hat. So the expression for our force, we'll multiply those two guys together, minus 9.48 times 10 to the minus 12, not 13, 12, times B down J hat. Okay, so there's that phase of the problem. We know the force on this particle as it's moving through the field. Okay, let's apply this force to find the velocity when it's down here at the bottom, when it's emerging from the field. So let's do a new diagram. So here's that first 0-volt plate. Here's the 10 kilovolt plate. There's the area with our magnetic field, where those magnetic field vectors point into the page. Our charge comes in, initially moving to the right, so there's our initial velocity. But it experiences a downward force, so it's going to deflect. If you're trying to imagine how this works, if you throw a ball horizontally, then it will start to deflect as it moves down towards the ground. This is not dissimilar to that. It's the same sort of motion. There's a downward force, so it'll start to move down even while it moves across. This is the same thing as projectile motion. So the overall path, so that's the original velocity. This is the path it will follow inside. So that'll be the path, and then this will be the final velocity. And we can use our kinematics to find that final velocity. As you're going through, you might think about what happens to the force, and the force doesn't change because it only depends on the x component of velocity. What happens in this y direction doesn't affect that force at all. So let's now find out that final velocity. what we'll get is, let's see, so V final has got an x component, V final x, and it's got a y component, V final y. Our V final x, there's no acceleration in the x direction, so V final x is equal to V initial x. So VFX equals Vx, which is what it was when it started. That was our 5.93 times 10 to the 7 meters per second. V final y equals V initial in the y plus the acceleration in the y times time. Okay, so let's see what these terms are. Vy equals 0. Initially it didn't have any y component. Acceleration in the y, first thing is it points down, so it's negative. If F equals ma, then A is force over mass. The force was minus 9.48 times 10 to the minus 12 times B. The mass is the mass of an electron, 9.11 times 10 to the minus 31 kilograms. Do this on your calculator, you get minus 1.04 times 10 to the 19 times B. There's the acceleration. Now how about the time? Well, we know that Vx is going to be distance over time, so time would be distance over Vx. The distance is the width of that path d that was given, 0.02 meters, divided by Vx, which was 5.93 times 10 to the 7 meters per second, gives us the time that it's in that field is 3.37 times 10 to the minus 10 seconds. Okay, so now there's everything that goes in our y equation. So we've got 0 plus minus 1.04 times 10 to the 19 times b. Remember, we still don't know b. Multiply by our time, 3.37 times 10 to the minus 10 seconds, gives us a final y component of the velocity of minus 3.51 times 10 to the minus 9b. And that's going to be in meters per second, of course. Okay, if you get here, you might have a moment's pause and say, hey, that's times 10 to the 9, which is bigger than the speed of light. That's true. But recognize here that it's this factor times b. What this is telling us is that b is going to be smaller than 1, because we know VFY is not going to be bigger than the speed of light. Okay, so we've got some insight now on what we expect for our answer for that magnetic field. Let's finish by putting our angle given into the picture. So there was our 0-volt plate, our 10 kilovolt plate, the magnetic field that pointed into the page, the original line of our velocity looks like this. Our final velocity looked like this, VF. That VF had components of VFX. These two guys are parallel because they're the same VF, the same speed. VFY, and this angle here, theta, is 10 degrees. Well, if we think about our trig, then tan of theta equals VFY, the magnitude, divided by VFX, the magnitude. We know theta is 10 degrees, so tan of 10 degrees equals VFY. Well, we had that up above. Remember, this is the magnitude. Divided by VFX, which we also wrote down up above. Now we can solve for our b. So we'll multiply this up here, we'll divide that one down there. What we get for the strength of our magnetic field is 2.98 times 10 to the minus 3 teslas. So there's the magnetic field to get that electron to deflect by 10 degrees.